Okay, I'll get started. Again, thanks to Tom and Joanna for inviting me virtually to visit UCL, and I wish one day I can visit the university or department in person. So today, let me try to entertain you by a talk that I've been given for quite a few times now, and again, any comments and suggestions are welcome. The title is Balancing Covariates via Propensity Score Weighting. So it is pretty generic. And again, given the audience, I know in about that audience, then most people know propensity score, know causal inference, but in a stat audience, it's not, I don't assume everyone know exactly the background and context, so I will spend a little bit of time in the background. Let me start. So again, causal inference traditionally, since the Ronald-Fisher time has been done with randomized trial, but we know, randomized trial because of practical and ethical reasons cannot always be done. So actually in the last 20 years, I would say that population-based observational data has been increasingly used for causal inference. Again, in medical and health research, it's usually known as comparative effectiveness research. Again, statistics known as causal inference, and econ is often known as program evaluation. So the key is, for causal comparison using observational study, the key thing is to balance the covariates distribution between treatment group and control group to remove confounding. So if you have two groups, they are similar, then you can draw, it's like in randomized trial, two groups are similar, then you can arguably draw a causal conclusion. Even that is strong. But of course, in observational studies, often the treatment group and control group look very different. So a common approach to achieve the balance is via weighting. So what is the main idea of weighting is I have treatment group and control group, and then I assign a weight to each unit, so that in this weighted population, I kind of created my weighted population. This is a pseudo population, a weighted population, which is essentially our target population where the two groups are balanced. And then I can make the comparison in that weighted population where the two groups are balanced. So the dominant weighting approach in the literature has been inverse probability weighting, or IPW, or Horvitz-Thompson. So I'll give a quick example, motivating example, just for illustration. This is very standard in causal inference. So this is a Framingham Heart Study. It's a very well-known longitudinal study on heart disease and on health behavior, and heart disease. So it's a follow-up already for ongoing for the last 40 years. A lot of important discovery about cardiology has stemmed from this study. So again, we're just studying a very small portion of that just for illustration. So the goal here is try to evaluate the effect of taking statins on health outcomes. And the patients, the patients are, the sample we have is a cross-sectional population from offspring cohort with visit 6. So this is just we define our sample. It's a cross-sectional sample. And then the treatment is just whether you take statins at this time versus not. And the outcome is, a bunch of health outcomes. Can be CV deaths or MI or stroke. So there are a bunch of confounders. Their sex, their gender, age, or BMI, all this standard confound, and particular history of MI. So if you look at the data, there's significant imbalance between the treatment group and control groups. So this is a graph to show how balanced things are. So you can see that here, so each row here in this graph, age is a confounder, it's a covariate, HDL, diabetes. And so let's look at the red dots. So essentially here, each of the red dots for each group, I calculate basically a standardized mean difference. So the bigger this value is away from 0, that means more severe imbalance. Okay, so you can see that. So the red is basically the raw data before I do any weighting or anything. So you can see that, okay, the data is really, and usually the standardized difference is 0.1 is kind of threshold for significance. So you can see that really there's a huge difference. You can read the dots, it's all over the place, right? So the age, like the starting group usually are older, and they have history of MI, heart disease, and they have higher cholesterol, you name it. Okay, so then then those purple dots are essentially used. I haven't introduced IPW, but I will. So IPW is just a weighting method, and once you apply the IPW weighting, and you can see that, well, so it's getting much better. So the balance of the weighted population is much better, but still it's not. There's still a lot of important covariates are not balanced. And then you say, this green one looks pretty nice. Yes, that's the point of this talk, partly point of this talk. So that's kind of the context. So now let's start to define something in order to go forward. So let's say we assume we have a random sample of n units from a population, and so for each unit, they're either treated or controlled. So I call Z 0, 1, and I have a bunch of covariates or confounders, observed confounders. Then for each unit, again in Causal Inference framework, we call that they have two potential outcomes, Y1 and Y0, each corresponding to one potential, like hypothetically, if they're assigned to that treatment. But of course, in reality, only observe one of the two. In Causal Inference, we often say this causal estimand essentially is a target, is a parameter, population parameter that you want to estimate. Again, a common estimand in the literature is the so-called average treatment effect, ATE. Essentially, that's just expectation of Y1 minus Y0. It's like, so hypothetically, you switch everyone to treatment versus everyone to control, then counterfactually what the difference would be. That's ATE. Again, I will expand over that. That's just a common estimate in Causal Inference. So I will make two assumptions. Again, you will say that this is strong assumptions, but for this talk, I will just make this standard assumption as 95% of the Causal Inference literature make, and then proceed under. So the first one is unconfoundedness. It's basically say there's no unmeasured confounding. So the second one is the overlap or positivity. Basically say every unit has non-zero probability being assigned to treatment and to control. Again, non-confoundedness is a very strong assumption. It's kind of fundamental, but we're proceeding under that. So to talk about that, that's basically a topic of another talk. So just bear with me. So once you assume this is all standard. Once you assume these two assumptions, then the ATE, the average treatment effect, which is defined on the counterfactuals or potential outcome, can just identify it from observed data. So instead, you can just, if you can balance the covariates, then if you conditional X, if you have balanced covariates, you can basically just calculate the difference between the treated group and the control group in terms of outcome, and then you can estimate the ATE. So that is all standard. So then what is weighting? Okay, so the inverse probability weight. So we need to introduce this thing called propensity score, which is the probability of each unit being assigned to treatment. It's a probability. So the base of the IPW is this equation. I'm not going to read it out, but essentially once you do the weighting like this, you can ask the expectation of the weighted mean of the outcome. It's equals ATE. So in other words, that you can basically define weight for each unit in the treated group. You define the weights as 1 over the inverse of the propensity score. If you're in the control group, it's just inverse of 1 minus p. Essentially, it's the inverse of the probability to treatment. And so you can define weights like that. And then because of this equation, unbiased moment estimator is just difference of the weighted average between the treated group and the control group in outcome. So then you get the ATE. Okay, that's all very standard. So what is really interesting is remember, we still talk about balance. I mean, you can do this, but what really what is balance here? So you can actually show, as I later show in a general framework, IPW actually what it does is it not only give you unbiased moment estimate, it also balance in expectations the weighted distribution of the covariates in the control group and the treatment group. Again, I will show this much clearer later. So this is all standard. People do this all the time. But there's some conceptual challenges of IPW. So first of all, remember I mentioned that when you do weighting, you weighted your units, weighted your subjects, and then created a weighted population, and then basically draw a conclusion on that weighted population. So this weighted population essentially is your target population. So it's very crucial to ask this question: what is the target population of IPW? Because you are reweighting it. So the IPW, it's turned out the IPW is basically the so-called whole population. Essentially, the study sample you have in hand, assuming it's basically implicitly assumed that it's representative of our meaningful population. And so the target population of IPW is basically the population that is represented by your study sample. Okay, so this is, but that's when people use IPW. But a very important, and people say this is the AT, average treatment effect, on this whole population. But a very common question, but people often ask, so that is essentially implicitly assume your sample is representative of a population. But the question is, what if it doesn't? Or in other words, we talk about ATE all the time, average treatment effect, our average treatment effect, but we very rarely ask what is the average on, what population the average on. It is essentially what is the expectation taking over, okay? So why do I say this? Because in observational study, very often the study sample itself is just a convenient sample, especially in medical study. It's just available sample is available sample. It doesn't really represent any natural population of scientific interest. Often I get a data from a hospital, and that's it. I don't know whether this hospital is Duke Hospital or UNC Hospital. I don't know whether it is representative of a national population. But people still just apply IPW without asking actually whether this is a meaningful population. And also, so in that sense, in that case, when your study sample is a convenient sample, then applying IPW to, does not lead to ATE to any meaningful population, right? So that's one thing. And another thing is, often I talk to my physician collaborators. They say that they don't have in their mind, they don't write down this ATE, this formula, right? So they say that this estimate doesn't make any sense, because for a lot of patients, they know exactly which way the patients cannot be hypothetically switch treatment. So because IPW actually, the definition involves, or the average treatment effect is, the definition involves for every unit, for every patient, you switch the treatment. Okay, so that is, sometimes just completely infeasible, because some patients can be only, even hypothetical, can be only assigned to one treatment. So if you only focus on IPW, then those patients, you get to average treatment effect that this doesn't mean anything. And of course, that is conceptual, and conceptual challenges exactly translate into operational challenges. Again, you probably all know that IPW, the history is from the Horvitz-Thompson, the survey weights from the survey literature. And because the definition is inverse, you can see that the key problem is when you have propensity score very small or very big, I mean, close to 0, close to 1, these weights will explode, right? This is very well-known problem. And then, in that case, then you have very bad, you have the variance is huge. You have when you have extreme probabilities, then the finite sample probabilities is really bad. So what people do is people say, oh, you can normalize your weights, basically make it the sum equal 1. That helps, but that doesn't help too much. So then the common remedy in the literature is to trim. I say that, okay, if I have extreme propensities or the probabilities, I just trim them, I just cut them. For example, I just restrict my propensity between 0.05 to 0.95, and it will be, the problem will go away. The problem of that is, first, you need to artificially choose a cutoff point. Depends on where you cut, the result can differ quite a lot. And second, when you trim, you are basically you start to limit your sample. And again, we mentioned that the key thing is the difference between sample and population. So once you start to modify your sample, what really does your target population, this new trimmed population corresponding to, you don't know. The biggest problem is again, this can be sensitive. So again, the core problem is this so-called lack of overlap. So if my study sample, or if my study sample, everyone has kind of in a nice randomized trial, then everyone's propensity would be 0.5. Everyone would have like equal chance being assigned to each treatment, right? I don't have that problem. This problem only happen, when we have some patients or some units that have propensity of being extremely likely to assign to one group or not the other one. So those basically in the tail of the propensity distribution. So those things we call lack of overlap. So the key point is that, when you have in the regions of this tail of the propensity, or in other words, that lack of overlap, we don't have enough patients of both treated and control in those tail distribution, then the causal comparison of those units is just very highly uncertain. So that's the main problem. So so that's a long kind of introduction, and the main point of this talk, 2 points, is first we kind of provide a unified framework called balancing weight to allow user-specified target population. And then the second one is, so the point is that you don't need to always just focus on the average treatment effect. You can focus on other population. The second one is within this framework, I will propose a new weighting scheme called overlap weighting that captures the overlap population and had some nice statistical properties. So this is a mass development of that. So first we will extend the definition of average treatment effect to the conditional, essentially define the average treatment effect conditional on a specific value of covariate. X, so it's just tau x, okay? And we assume the density of the observed covariates, the density of the observed sample about the covariates, fx exist with maybe respect to a measure. And then the key point is we're gonna introduce this concept of target population to say that, okay, this is observed sample, observed population. But let's say we have a target population. This might not be exactly the same of the observed population. So let's call it G. So the G is basically just, it's G, it can be written as fx, the observed population, times this thing I call tilting function. It's just, this is a target population, it can be any function. It can, and then you just calculate the ratio is called the tilting function, right? So why I call it tilting function is basically this function tilt your observed sample, observed population to the target population, okay? This is just definition. So now I can define my ATE, average treatment effect, instead of just on the observed population, I will define it on a target population. So this is, again, similar as before, it's just expectation of this conditional average treatment effect, but on a target population. So in other words, it's just a weighted version of the it's a weighted average treatment effect. Okay, so we can weight, basically we can weight to any population. Okay, so then you ask, okay, well, so this is my new estimand. So I can, again, think of H equal 1, which, you're just being to the old, then we're back to the old average treatment effect. Okay, so then what is balancing weight? So let's say now this is our estimate, this is our target estimator, target causal parameter we want to estimate. And the key equation we realize is this. So we can define the conditional probability of the conditional distribution of X of the covariates in each group, in treatment group and control group. We define it as F1X and F0X. I just denote, sorry, not define, just denote it. So the key realization is this for F1, basically the conditional distribution of X in the treated group is proportional to the Fx, the distribution times the propensity score, the EX. And for the conditional distribution of covariates in the control group, it's just proportional to Fx times 1 minus EX. So why this is useful is because, remember, now this is our estimand. So remember, the idea of weighting is try to re-weight your observed sample so that it is in the weighted population, it is balanced, right? So then fine. So this is my, this is my target population, my G target population. So now I just re-weight, I need to find those weights so that, I assign the weights, then the average of my treated group and control group will be balanced. So you can just, this is my target population and this is the treated group, right? I can just get the ratio of the two, which again, because of this equation, is just HX divided by EX. And same for the control group. I can just weight my control group to the population, to the target population. I define weights this way, and because of this equation, it's just X divided by 1 minus EX. So any weights, so now this is nice, because then for any HX, for any target population, which is equivalent to the tilting function HX, then I can define our weights in this fashion, so that by definition, I actually know that the weighted distribution of the treated group and the control group will all equal to the target population. Okay, so that is, and this is why it's called balancing. I call it balancing weight, and this holds for any function. Of course, some smooth function you get. Well, actually, even non-smooth function is fine. This is holds for any function. So HX. So then you can see that for any HX, then it defines basically the S demand, because HX, the tilting function defined the S demand, the target population, the S demand, and also the weights. Okay, so the key thing is, okay, what are the H we people use? Well, think of H is 1. Think of H as 1. That is, essentially saying that the observed, so the target population is represented by the observed sample. Then when H is 1, what is its weights? It's the IPW, the Horvitz-Thompson weight, right? But that is, we all know that's not interesting. So now you can also say that, well, if let's say my target population instead is the treated population. Again, in econ or in medical research, it's very often they're interested in the average treatment effect was treated units, or treated patients. So in that case, how do I reach that? Then in that case, my target population would be, if it's the treated population, is basically F1X. So then your HX is basically proportional to EX, right? So if then in that case, your target population is your treated population, and then you can define weights. So just to use this formula, define weights, basically for the treated unit, you don't do anything for the control, you weight them by the EX divided by 1 minus EX. Again, this is directly derived from this equation, the balancing weights, right? Then let's say that if you're interested you're interested in the control group, yeah, well, your HX, your tilting function is just 1 minus EX, and then you can define weights accordingly. And also let's think of trimming. What trimming does is trimming, if you get rid of the extreme weights, essentially the HX just become the indicator functions that are defined as a range of the propensity score. So those are all, people are used. So the key point of this talk is we're going to define a weights called overlap weights that is obtained by setting the H function to E times 1 minus EX. So I will reach there. So in order to reach there, we need to do some large sample derivations. And this is, again, nothing fancy. It's just purely a device to reach to my conclusion. So remember, we know that before, so why do a weight? So now we obtain the weights defined this way and derived this way, and we know that it will balance the treatment group and control group in the weighted population, in the target population, right? In the target population. So then the first question is, how do we estimate this new estimate on this target population? Well, that is, just a weighted, essentially. You guess you bet it's just the difference of the weighted outcome in the treatment group and the control group, and this is the moment estimator of the weighted average treatment effect. And of course, the first one is consistent. This is nothing special, right? So the second theorem is a little bit messy. I think you don't even need to read this. Essentially, I just derive, I derived the large sample variance of the estimator. So there's some technical issue, but what is really important is to look at the corollary of this theorem. So this result basically say that among all functions you have there, again under some regularity conditions, but very, very mild, among all the tilting function HX there, or basically among all target population, the function that EX times 1 minus EX will give you the smallest asymptotic variance for this weighted estimator. Okay, so that is, again, this whole messy slice, just the key conclusion is this one. Remember here, we're kind of moving over goalpost. People in causal inference, people always just talk about ATE, average unit effect. There's always, one target population. So I'm here kind of moving the goalpost a little bit. So we're saying that we can actually, when you have a sample, you don't need to always just look at the sample itself. You can look ahead, you can look differently. I think there might be different target population. You can look at, and among every time you choose a different HX, you basically define a different target population. And among all this target population that defined by this equation, this equation actually will give you the smallest asymptotic variance of this weighted estimator. Okay, so we're basically shifting goalposts to find the optimal target population in some sense. Well, actually, it's weights. So I will get to more point of what is scientifically, what does that mean, right? So now the thing is, based on this result, we can define a new type of weights. So we call it overlap weights. Basically, with this, given the HX equals this, then the weights is no longer inverse. It's just, well, this is proportional too, because you have to normalize them. So this one essentially just, what is this? So this is to weight each person by its probability of assigned to the opposite group. It's no longer the inverse, but it's assigned to the opposite group. Okay, so then you would ask me, okay, this is mathematically defined, and what is really the meaning of this population? Well, this population essentially are so let's first look at this. So the propensity is quantity between 0 and 1. So among all the propensities in the whole range of propensities, which value of the propensity that the maximize HX? Okay, this is a simple question, but you probably know it's 0.5. Right? And actually, as it's 0.5. So, and as your propensity goes towards 0 and 1, this H function or this tilting function will get smaller and smaller. So in other words, the weights defined by this overweigh, this is probably the best, it's look at here, it's overweigh the units in the middle, in the sense of that they have equal probability of being assigned to both treatment. And then there will be gradually downweight as they get closer and closer to, be assigned to the extreme, or they're more and more likely to be assigned to each of the two groups. So the target population of this overlap weights really is the units whose characteristics could appear with substantial probability in either treatment, or essentially they're in most overlap in that sense. So this, if you notice that actually the EX times minus AX is also harmonic mean, and also it's a Gini index in the classification tree literature. And so this function looks a little bit strange, but it's really means the population with the most overlap. Again, I already hopped on here to describe what it looks like. I generate, just to showcase this, I generate two groups. Let's say we only have one covariates, and then I generate the treated group. The control group is this red line, and the treated group, is this green line. So you can see that they have some lag. There's a shift. So this is really the overlap. Only in the middle there's some overlap, and as they goes to the X goes to the edge, then the groups really start to look different. And then if you look at the propensity, so this blue line, so this dashed line is just the unweighted population, the combined population, and the blue line, after I weight by the overlap by this tilting function EX times minus EX, you can see what it really does is, again, overweigh the patients, overweigh the units in the middle. In the middle, again, means that the propensity close to 0.5, or the population that have substantial probability being assigned to each group, or the population on the fence in some sense, and then it gradually downweight people in the in the edge as the overlap gets less and less. So in other words, you can see that overlap weights is almost a continuous version, can be viewed as a continuous version of trimming. So instead of 0, 1 throw out the extreme propensity, I continuously downweight them. So the let me see. So then this is well, let me actually go to a little bit more to talk a little bit more about the scientific relevance, or what does this population really mean, and then I go back to some to the more properties. So overlap weights really, as I mentioned, the focus on the subpopulation actually in some sense closest to the population in a randomized trial, because in clinical equal, so in the I think in medicine, the patient, if you do a randomized trial, a very important principle is called the patient must be in clinical equipoise. The point is that you cannot, if you know a treatment works better for certain patients, then you shouldn't ethically, it's not ethical to randomly assign them to a randomized trial or to any treatment, right? So the idea is, the principle, the ethical principle in randomized trial is the population you do a randomized trial on must be the population that the doctors a priori have no information about which treatment works better for them. Okay, so then this is essentially the target for the overlap population, right? The population has the most overlap, you don't know. Because if you are, for those patients in the tail of the propensity, or they have a very large propensity close to 0 and 1, essentially the doctors know what treatment they should be in. So then in that sense, those patients will never enter a randomized trial. So in this sense, that overlap weights, the target population of overlap weights is really kind of reminiscent, mimic randomized trial, the patients in a randomized trial. And so in policy, this overlap population is also important because they are most likely being responsive. So those are the kind of the people who are on the fence. So when you have a new policy shift, new policy come in, then there's new information coming about a particular treatment or policy, then those are the people who are most likely to change their behavior, right? If your propensity is close to 0, 1, so you would never change your behavior. So this is also in policy, those are the other people with the most, of most interest. And also in racial disparity studies, similar. You want to compare the group, the different racial groups only if they are, only if their socioeconomic status are very, or general background are very similar. It doesn't make any sense to compare, minority group very poor and with a white population and very rich. So the point is that the overlap population is often actually the most important or most scientific and meaningful population there. I'm not saying always, but it's often. So that is the definition of the overlap weights. And then so overlap weights is derived because of the asymptotic variance from the variance consideration. So it actually also happened, and that's large sample. And then later we showed actually it also has a desirable small and finite sample property called exact balance. So this is a very cool result. It's, the propensity. So most of the time, the propensity score in observational study, you don't know, it's a probability. So you have to estimate it. And so most time propensity score, again, in applied study, people use logistic regression. Looks like this, logistic regression to estimate the propensity score, use maximum likelihood, right? So what we can prove is actually overlap weights. Once you estimate the propensity score from this logistic regression, and you define you calculate your overlap weights based on this estimated propensity score in this form, then it will lead to exact mean balance in any of the covariates that is in this model. Okay, so and that holds exact. So this is expected value. So you just estimate your propensity score, use this model, and then whatever covariates you throw in there, the overlap weights calculated based on the propensity score estimated from this model will be, balanced. Will be balanced, mean balance. So that is, and this applies to any derived covariates. Say if you have age, you provide you put the quadratic term of age, then it will always balance overlap weights will also balance the quadratic term, and interaction term you put there, it will also balance that. So now let's go back. So, and the proof of this is actually pretty simple, and this is it's only hold for binary, but in the multiple treatments is actually getting close, but it's just not exact. So now let's go back to the original graph I show you, the balance. Remember, we say that, well, this green dots looks pretty nice. So essentially here, each of those dots is basically the standardized balance. And if you have the exact mean balance, so this would be exactly 0. The balance would be exactly 0. And then so not surprising, overlap weights is almost close to 0. And of course you say that, well, if you find a sample property, then why this is not exact 0, why there's still some differences? Well, it turned out that the key is, use maximum likelihood, and here we're using splines, so that's why it's not exact, but you can see overlap weights actually get very close to 0 balance. So in other words, it gives you the quote perfect mean balance. And this is just a mathematical result, but empirically, actually intuitively, this makes sense. The reason is overlap weights really focus on the people in the middle. So the people in the middle are, they have the most overlap or most overlap in their covariate distribution. So just intuitively, they should be very similar. Okay, so that is intuitive explanation behind that. And again, this turned out to be also very useful if you study subgroups. I'm not going there. And now just quickly summarize what is statistical advantage of this new weights. So first, it's just by the derivation, how I define that, it has a minimum variance among of the nonparametric moment estimator among all balancing weights, and it gives you exact balance. And a nice thing of, if you look at this weights, the defined, it doesn't involve the inverse, right? So it's bounded. It's bounded between 0 and 1. You will never have extreme weights. When you have this extreme propensities, it will only be gradually downweight. And if you are the close extreme propensity will only be downweight towards 0 instead of blow up your weights. Okay. And another thing is, it's really, as I mentioned, that it can be viewed as a continuous version of trimming. So you don't really artificially, don't like 0 and 1 throughout the trim some units, but you continuously downweight them. So that way you basically avoid ad hocly setting up a cutoff point and eliminate it and throw them away, right? So then, for overlap weights, I don't need to worry about, oh, I choose different cutoff points, then my result would be jump around. And I do have an example actually later that depends on where you trim, the result really can be different. And in overlap weights, because it's continuous, you never need to set that. And also it turned out that a recent study to show that, the overlap weights, when you have, all of this propensity score weighting thing is important. You need to estimate the propensity score. So a recent simulation study show that if the propensity score is misspecified, there are always all sorts of issues, but overlap weights, again, because it focuses on the patient in the middle, it's less sensitive than IPW when the propensity score model is misspecified. And those are nice statistical properties, but really more important to me is this mathematically defined new weights, equivalent new target population is also scientifically meaningful. And I already just went through why it's scientifically meaningful, because it's a most overlap population, and it's useful in medicine and in policy, and in many cases. So so I just mentioned this because now we're living in the COVID-19 era. So overlap weights, because it mimics attributes of a randomized clinical trial. So it's like it take a sample, but then focus on the population that is most reminiscent to a randomized trial. So it's very useful. So it's useful in the situations where large randomized trial is not immediately available. For example, the COVID-19 study. And I'm saying this is because this point has been made in a recent JAMA cardiology paper editorial calling using overlap weights as a primary statistical method to dealing with the analysis of COVID-19 at this point. Again, I didn't make this up. So now quickly just to show some of the show some operation characteristic of what all these weights, different weights are doing. So just to show you, so I generate a very simple example, have two groups, and each group have 1,000 units and have a single covariate. We can think of this covariate as something like an age. So the scenario is the treatment group and control group, there's almost perfect shift. They are quite different. And so the outcome, I generate the outcome. It's a function of the covariates. It's highly related to the covariate, predictive of the covariates. And again, in this case, I generate every unit have exactly the homogeneous treatment effect. It should be 1. Okay, that's how I generate it. And then I will, because remember, every time you're talking about different target population, the true estimate can be different. So the way I generate it here, so that it's a homogeneous treatment effect, then the estimate is the same for every for all the target population. So you can see this is a saying this is really a graph to show you what IPW and overlap weight does, and HT is just Horvitz-Thompson, essentially IPW. So you can see that this is a distribution. So this is a weighted density of the weighted covariate distribution. Here, because I only have one covariate, so I can just draw a histogram. So you can see that in the raw sample, the treatment group and control group, has a shift. They're quite different. They have a shift. And overlap weights, what it does is once you get the weighted covariate distribution density, then it is more or less the same. That's what a balance is trying to achieve. So you can see that Horvitz-Thompson or IPW is doing something really strange. What it does is try to drag the population in the tail. What mean like tail? Like those are where you don't have overlap, but the treatment group and control group look very different. And what Horvitz-Thompson or IPW try to do is try to artificially actually overweigh those people in the tail where there's no overlap. And this is what Horvitz-Thompson, what IPW try to do, and in the end, you can see that the end is weighted. In the end, even though in expectation, the treated group and control group, the covariates should be look similar, but that's only expectation. If you really look at the raw distribution, the weighted distribution, you can see that this really looks very different and very weird. And if you look at the ATT, average treatment effect for the treated group, it's doing the same thing as IPW. It's just instead now it's doing it, try to overweigh the group in the control in the tail population in the control group. So you can see that's what they're all doing, and then we can just calculate we can also see this is just about the covariates. It's not even about causal estimate. And then because of this large variance, so we can see that also in terms of point estimate, the overlap weights is exactly the same. It's unbiased for the true treatment effect. And IPW and the ATT, both of this are doing really terrible because they're like 40% off or 30% off. And the reason is because you can also look at the variance of the estimator. It's huge. So the IPW is almost tenfold than overlap weights. And this is not surprising. It's because that's exactly when you have lack of overlap, which is the key challenge in any causal study. You can see IPW is just doing something not sensible. So now we go back very quickly, go back to the original Framingham study, and I already talked about this graph. So you can see overlap weights achieve much better balance. And now we can also see, okay, this is just look at the propensity. So you can see that what is the population. So again, Framingham study has many covariates. So very common technique in causal inference just to look at summarize the treatment group and control group is just to first calculate the propensity score. Then this is a one-dimensional summary of all the covariates, and then you draw the histogram or density plot to see how different they are. So you can see that here this is a study that the non-statin group or the treated group has like tenfold more than the statin group. So the propensity of evidence propensity is pretty small. So you can see that here the black dashed line is just the control group. So their propensity of this is a propensity of taking statins. They are pretty close to 0, or well, it's kind of around 0.1. And the statin group is this red group. So it's this red dashed line. So you can see the red line really it has much long tail. So there are people who are whose propensity of getting it is very high. The key point is that you can see the treatment group and control group look very different. And then you can see that actually the IPW, what IPW does is it's pooling the whole population still, the target population. It's just a weighted average between the treated group and control group. But you can see the overlap weights is much closer to the treated group. And there's a mathematical reason behind that. I don't have time to get there. But the point is that in causal inference, people very often draw this kind of graph to visualize the difference between the treatment group and control group. So another thing is you can actually characterize the target population, even though it's mathematically defined, using a table like this. It's basically for each group, and this is very often called table 1 in medical papers. So in this paper, in this table, it's for each row, it looks like this. Each row is a variable, and then you can have the unadjusted difference between the treatment group and control group, and then the overall group. And then you can also plot the adjusted after weighted. So you can see that, okay, the IPW weighted or the IPW with the trimming and the overlap weighted. So you can see that there's a difference in the target population. So this is just a way of to show you that how to characterize the target population. And then the result is again, we have several health outcomes. So I just show you one. So this is, again, statins in randomized trial. There are plenty of randomized trials to show that it's beneficial for health to reduce the overall mortality. So you can see that in this case, if you don't adjust any covariates, just calculate the difference, raw difference between treatment group and control group, then the results say, oh, statins is bad for you. Of course, we know that this result is highly biased. So you can see that then if I use IPW, well, some people call it IPTW. So IPW, you can see that the point estimate will also be very close, will be over 1 at always, and also this large confidence interval. We say that statins will kill you. But then you can see that, well, if you do overlap weights, so if you do trimming, the key thing is if you do trimming, if you want to fix IPW, then you trim it, the propensity close to, if they're beyond 0.1 and 0.9, you trim them. So you trim them, then the results become much more reasonable. But the problem is depends on how you trim and where you trim. The result, you can see this is different trimming rule. You use asymptotic, symmetric or asymmetric. You can see it depends on how you trim, where you trim, the result just jump around, right? But with overlap weights, again, it has the shortest confidence interval, which is not surprising because theoretically we proved that. And second, that it's much shorter. And second, you don't really need to set any artificial bound there. And then it just give one point estimate, and it's close to, and it's below 1. Again, this is just purely illustration. This is a well-known kind of medical. The medical conclusion is pretty well known. This is just to show you the illustration. But you can see that overlap weights again give you shortest confidence interval, and you don't need to trim. So that is. That is our example. So now it's time, there's several extensions of this, and I'll very quickly wrap up. So overlap weights, of course, we can extend it to more than just 2 treatments and use, generalized propensity score idea. And it's also very useful for subgroup analysis because of the corollary because of the exact balance property. And another thing is, propensity score is often used as it has been developed in the context of observational study, but it happened to be also very useful as a covariate adjustment approach to correct for change in balance in randomized trial. And this is a different, this is quite a different route, but the operational is exactly the same. And currently we're extending it to time to event outcome, continuous outcome, continuous treatment, and cluster data. And just a quick history note again. So this original paper I wrote with Alan Zaslavsky, who was my postdoc mentor. So originally he already conceived the idea of this around 20 years ago, and then he convinced his collaborators at Harvard Health Policy to use this. So since 2001, in quite a few high-profile medical papers, people use overlap weights. Well, actually most Allen's collaborators, but it's very funny. You don't see it's really defined in mathematical way or any theory development. It's just a one medical paper. There's long medical papers, well, actually short medical papers. In the method section, there will always be one sentence say, oh, we weight the propensity. We weight each unit patient by its propensity being assigned to the opposite group. And so people never know that, other than very few people. So then in about 5 years ago, we write this up and develop the theory, and then we actually extend this, find a lot of interesting things beyond that. So that's why only in recent years this has been, people start to use this more widely. But again, Allen had this idea first. So we also had a package. Again, I say that the propensity score, if you use IPW, then overlap weights is literally a single line change of code. You just change your original weights from IPW to overlap weights. So it's very simple to implement. And then you'll ask me, why do you still write a package? Yeah, the package is that, well, we will still use IPW and you are trimming. And of course, we're only talking about point estimate. What about variance estimation? And what about double robustness estimator? And if the outcome is a binary or counted outcome, you might not want the average, you want some ratio estimate. How do you do that? Stuff like that. And how do you draw those nice plots? So we wrote a package, and it's on my website. So let's just quickly give a summary of what we have done. So we proposed a unified framework for balancing weights to balance covariates for any target population, not just the population represented by your study sample. It can be any population that you specify. And within this framework, within this family of weights, we propose the overlap weights, which asymptotically minimize the variance and give you exact balance. But the key thing is, scientifically, it mimic a target population in a randomized trial. In other words, that if take observational study and try to actually find the meaningful population, most meaningful population in this, or the population with the most internal validity in this sample. And that's what overlap weight does. Again, it's very simple to implement, literally one line change of code from IPW. So the takeaway is really, again, I'm not saying that you should always use overlap weights. The point is, as a statistician, it's always important to, before you do a study, do a causal study, it's always important to consider what is scientific appropriate target population before you just automatically shift to IPW or to ATE, because the populations, this really is important one in the case that your population is heterogeneous, and most of the time our population is heterogeneous. Different subpopulation have different treatment effect. So when we always just automatically focus on average treatment effect, we'll kind of lose the point. Instead, you should use overlap weights or ATT weights and IPW to see that whether, if the results are very different, this is actually also strong evidence of there's a heterogeneity in the treatment in your sample, in your population. Then it's even more important to report just just report the result of ATE. So, and always also when we communicate results to the doctors or to the physicians or to our collaborators, it's also important to say, hey, this is average treatment effect on a specific subpopulation, and this depends on what subpopulation is. The result can be different, and this is just, I think, is an honest way of doing causal inference or statistics. And so I have all the material. I have a website on my webpage of more information, and I have there's a bunch of my collaborators here, and those are the key references.